The atom is made up of protons, neutrons and electrons. Their masses are listed as follows. Proton, 1.67 times 10 to the negative 27 kilogram. Neutron, 1.67 times 10 to the negative 27 kilogram. Electron, 9.31 times 10 to the negative 31 kilogram. We define the following terms. Atomic number. The atomic number of an element is the number of protons found in the nucleus of an atom of that element. It is a unique identifier for each element on the periodic table. The atomic number is what distinguishes one element from another and determines its chemical properties. Atomic number is equal to the number of protons. Atomic mass. Atomic mass is the average mass of the atoms of a particular chemical element. It takes into account the different isotopes of that element and their relative abundances in nature. Isotopes are variants of an element that have the same number of protons, and thus the same atomic number, but different numbers of neutrons in their nuclei. Atomic mass is usually expressed in atomic mass units, AMU, or unified atomic mass units, U, where one atomic mass unit is defined as 1/12 the mass of a carbon-12 atom. For most elements, the atomic mass listed on the periodic table is a weighted average of the masses of its naturally occurring isotopes, taking into consideration their relative abundance. The formula for calculating atomic mass is atomic mass equals mass of isotope 1 times abundance of isotope 1 plus mass of isotope 2 times abundance of isotope 2. For example, the atomic mass of carbon is approximately 12.01 U, which takes into account the isotopes carbon 12.0000 U, and carbon 13.003 for U, along with their respective abundances in nature. The mole. 1 mole of a substance contains 6.023 times 10 to the 23 particles. So 1 mole of hydrogen atom would contain 6.023 times 10 to the 23 atoms of hydrogen. 6.023 times 10 to the 23, denoted by AE sub n, is known as the Avogadro's number. The mole concept is similar to the concept of the dozen, as 1 dozen contains 12 eggs. This means that there is a way to compute the number of particles to the number of moles. We can create the conversion factor knowing the ratio of moles to atoms is 1 mole has 6.023 times 10 to the 23 atoms. Example, find the number of moles if the sample contains 5.5 times 10 to the 22 atoms. We can solve this using the formula X atoms times the quantity of 1 mole divided by 6.023 times 10 to the 23 atoms. We have 5.5 times 10 to the 22 atoms times the quantity of 1 mole, divided by 6.023 times 10 to the 23 atoms, is equal to 0.088 mole. We now formally relate atomic mass unit to the molar mass using the Avogadro's number. We take note that 1 AMU is 1 proton, and a proton has a mass of 1.67 times 10 to the negative 27 kilogram. If we are asked to find the mass of 2 protons, we will just multiply its mass by 2. If we are asked to solve for the mass of 1 mole of proton, we will multiply it by the Avogadro's number. Example. Find the mass of 1 mole of hydrogen atom. 1 mole hydrogen times 6.023 times 10 to the 23 atoms per mole, times the quantity of 1.67 times 10 to the negative 27 kilogram per atom is equal to 1.005 gram per mole hydrogen atom. This is the molar mass of hydrogen. This is a little different from what you can see on the periodic table because the value on the periodic table uses the average atomic mass of hydrogen. We now define the molar mass. The molar mass is the mass of the substance per 1 mole of that substance. With the concept of the molar mass firmly established, we can now use it to compute for the number of moles given the mass of the sample. We can use the formula shown below to solve for the number of moles in a substance. N is equal to mass of substance divided by molecular mass of the substance. With this bridge, we now have a way to calculate the number of atoms, the mass of the substance, and the number of moles. Another functional relationship that works well in gases is the fact that 1 mole of any gas will occupy 22.4 liters of volume. We can create a ratio of mole to volume that will serve as our conversion factor that can solve for the volume, amount of moles of air contained inside it, and its mass. Remember that it should conform the STP condition, else this relationship for mole and volume in gases won't hold.